Today we are going to do section 1.9. So first let me show you some, scan the textbook. Here is the answer sheet that I've already showed you earlier. Doesn't hurt to show it one more time. Okay, and then this is the first page, which I have already showed it to you in a previous and in the last section. Again, doesn't hurt to show it to you again. Okay, next, page 44 and 45. Let's look at this stuff. Okay, and let's see, that's the whole page. Okay, and this is the top of the page, and then the bottom of the page. All right. And finally, page 46 and 47. First, the entire page, a little closer, I guess. Okay, and then the top of the page and the bottom of the page. All right, that should do it. So now let's start. Now, before we delve into the subject, I want to show you, review some of the old concepts. The first one, the binomial theorem, which is the expansion of something to a lot of power. Okay, you might remember this. If you don't, here it is. And I just want to refresh your memory. So when you multiply stuff that's to the different powers, right? X to the power 5. Remember this triangle where it goes 1, 5, 10, and 10, 5, 1. And generally speaking, the x plus y to the power n is expanded by something called the binomial theorem, as shown here, where the parentheses nk stands for something called n choose r. Okay, and let me show you the definition of n choose r is given here. Is something about choosing, okay, the number of stuff. Now please look into this in detail. Now for me, I've always had a tough time remembering why the binomial theorem works as n choose r. So here's a little explanation I wrote for myself. I don't know if it'll help you or not, but I just want to show it to you. Anyway, so if you don't know the binomial theorem very well, please review it because that will be necessary for this section. And the next thing I want to show you is the Taylor theorem, which from Calculus 2. Okay, a quick reminder of the Taylor's theorem. First, we remember the Taylor's theorem is that big long list of functions and various derivatives, and goes up, right, and divided by the factorial, etc. That's the Taylor polynomial, also called the Taylor expansion. Specifically, I want you to remember that if it's developed as 0, which means if you set a equal to 0 in that equation, then it's called the Maclaurin polynomial, which will be required in the homework. Okay, they will ask you about the Maclaurin polynomial, and you should remember what that is. Now, the Taylor's expansion has a remainder formula. So the remainder then is equal to something like this. It's the n plus 1th derivative evaluated as c, and so on. We'll go into details. I just want to quickly remind you of this thing. And finally, we need to remember how to do integration by parts. Now, integration by parts is done by the good old formula where u dv equals to uv minus v du. So that will also be required in this section. Now, having said that, let's turn to page 43 of your book, and we'll start talking about the Taylor's theorem. And the original Taylor's theorem is written here as the function of one variable. Okay, it is repeated here as well. It's the same as what we learned in Calculus 2 that I just showed you, and except now it's written in the summation form, so it's more compact. However, the book is going to prove this thing with I don't think we learned it in Calculus 2, but by proving it with integration by parts. In any case, it just says, well, if you prove it, if you do integration by parts, everything will come out very nicely. Okay, and that is the book's proof. Now, that is that obvious to you? Because it certainly isn't obvious to me. So what I want you to do is do this this proof as like a homework problem, whereas the integration by parts will be your hint, okay? And and so please use integration by parts, like it says, and prove Taylor's theorem for one variable, and also show that our zero and so on, everything will work out. Now, now after you've done that, let me show you what I did. Okay, to prove Taylor's theorem in one variable, give me a second. I need to find it. So here's what I did. I just did some copy and paste stuff from Calculus 2. Okay, so here I'm proving the Taylor's theorem as the book says. First, this is Taylor's theorem as stated. Okay, a bunch of stuff added together, plus the integration as at the end. But this is what we're trying to prove. Now to prove it, first we let our n equals to that thing at the end there. Okay, and then we'll apply integration by parts like it says. Now, how are we going to do integration by parts? We will have the question of all integration by parts is what are you going to call u and what is called v. Now, notice that my dv is missing a dt there. Okay, just pretend there's a dt at the end. So anyway, we'll let u equals to the second part, x minus t n over n, and then dv will be the fn plus 1t dt. So then du, okay, take the derivative, we'll end up with this thing. Don't forget the negative sign. Whereas v will integrate that derivative, which will reduce the derivative by 1. Okay, so far so good. Then following the integration by parts formula, we have then our n of x then equals to this stuff. And that's exactly integration by parts formula. Now, and then which end up, when you evaluate it, it will become this thing right here, which is, I believe, exactly what the book says. Yep, that's right. See, now we have gotten the part where your book says that our n is equal to this thing, okay, and then knocked it down by 1, so our n plus 1. So we have some kind of a recursive situation or induction situation going on here. So then we will continue doing that. We've gotten to this part, so far so good. And repeating on this process, then we have, we'll write the whole thing out, okay? Then we have, see, our n then equal to the first one, okay, then the second one is 1 less, and go all the way down to 2. Okay, when n is 2, then the r is 1 less, as you can see. Okay, see on top here, our n is equal to this stuff, and then our n minus 1. So when n is 2, then you plug it in, then it becomes, let me see. Actually, that's correct, okay? Although it might look slightly confusing at first. So we have the final term, okay, and then n will be 1 less. So eventually we got down to 2 minus 1 is where the derivative has just 1 left, and then whereas r will become 0. Okay, the last term is going to be 1 less than what's up here. Anyway, so eventually, we have our 0. What is our 0? Now, by the definition of our n, then our 0 has to be, we have n equals to 0 in the formula, and then we have, then it equals to this, okay? Is because everything else will be gone, and all we have is just the integration left. And so what we have then is, let's see, yeah. So from this formula, plug in n equal to 1, okay? And then, or something. Anyway, right. Anyway, so our 0, if you plug the value as being 0, okay, then all you have just the function itself left, this thing. And so when you evaluate it, that is f of x minus f of a. All right. So then our n, then if we rewrite this equation, it will be equal to all this stuff, and then minus f of a, okay, and then plus f of x. So which is exactly the equation that we were trying to prove. This is the Taylor expansion. See, if you put the summation sign on the other side. So we have therefore finished the proof as is shown in the book. Okay, yeah. So that takes a lot longer than what the book says. Do you see? The book just wrote it in some quick short formula, whereas we have to write the whole thing out. Okay, it takes a whole page of stuff. But it doesn't matter how you do it. It's important to do this so that you make everything clear in your mind, right? What's actually going on here. So please make sure you do this yourself. Okay, and then we will move on. Now, in the advanced books, they often the whole book reads like one math problem after another. And the way you do it, you don't read it like the basic math books. You treat each thing like it's a math problem, and you work it out yourself. And the book just gives you sort of highlights or hints at how to proceed, but it's your job to actually like bulldoze the thing, okay, to actually do all the real work. So anyway, so let's look at the next page. Let's consider the remainder. Okay, to look at the remainder, then we have to look at something called the mean value theorem, which was proved in basic calculus as well. But we will repeat it here. Theorem, which says that if you have some functions that are continuous and you have gx that's bigger than or equal to 0, then that integration situation happens where if you have the multiplying fx times gx, you can yank fx out of there. Okay, so that you have with the values, picking the value of a specific big X, where big X is between A and B. So then you end up integrating just the small gx, which is usually simpler or more convenient for you. Now the proof of this, it requires several theorems also covered in basic calculus. First is the extreme value theorem, where if you have a continuous function on a closed interval, then the function will be able to achieve its maximum and the minimum values. So therefore, we'll call those numbers big M and small m. As a result, then being the f can reach it, f is bounded between those two values, and then this inequality then applies. Okay, since f is between small m and big M, and then if you slap the integration sign on here, okay, and then this will be true. Then divide everything by the integral of g, being the small m and big M are constants, so you could pull them out. Then the next step is you get this inequality. Now at this point, then we have, that is, we're going to write down this thing, okay? So we'll choose big X between A and B such that f of x is exactly equal to that fraction, because that is possible by the intermediate value theorem. Okay. Now, once we found that, then this equation is that's the same as this equation. That is rewriting. Then it becomes this one. Okay, because the f of big X equal to this integral divided by that integral. So we have quoted both the extreme value theorem and the intermediate value theorem, which isn't proved here for now, but we will deal with that later. Okay, this is just a quick mentioning revision of the mean value theorem from basic calculus, which we're going to need to do the remainders. Okay, so I also want to mention that in this theorem, you can, now that we know this, we can also let g equals to 1, in which case if g is equal to 1, then the integral of f of x from a to b is just f of big X times b minus a. Okay, because g is 1, so you can do the integration right away and come up with that answer. Now next, let's look at the Lagrange remainder, which says that we will, for the Lagrange remainder, we're going to take g of t equals to x minus t over n factorial. So to prove the Lagrange remainder theorem, first let's remember what was the remainder. As we did earlier, the remainder is this thing right here, this integral. So it have f, and then the x minus t to the power n, etc. Okay. Now we're going to apply the theorem that we just looked at, this one here, to the remainder theorem. So as a result, we will pull out the f, just like it says, with replace it with a big X. And then, let's see, where is it? If we do that, then, so then once we do that, then see, the f part got pulled out and replaced by a big X, just like this thing says. Okay, so the remainder now, it looks like this, and we just need to calculate the integral itself. So please do that as I have done here. To calculate the integral, the integral itself is not hard to calculate because it's just a polynomial. So although you need to pay attention to when g is positive or negative, because the theorem does require that g be bigger than or equal to 0. So as a result, you take care of that, but there's some details, but it turns out to be the same either way, see. And so once you take care of the details, then you have shown that the Lagrange remainder is this thing right here, when all is said and told. So whether g of x is bigger than or 0 or less than 0, the answer comes out to be the same, because the negative sign kind of canceled out in the process. If g of t is negative, and so you have to slap on the -1 to the power n, but it all seems to work out. Okay, so please work out those details yourself. The next thing is the Cauchy remainder, which I don't even remember talking about in basic calculus, but it doesn't matter. Okay, in the Cauchy remainder situation, we'll yank the whole f out. That is out of the theorem. That is, we'll take g as g of t equal to 1, and everything inside will be pulled out. So the whole thing has a big X in it, right? So we have this thing, and that's the Cauchy remainder, which looks similar to the Lagrange remainder, slightly different, might be useful in different situations. So that's how you apply it, just with g of t equal to 1, and then and the whole thing inside becomes f of t, and you just pull the whole thing out, and that's what you get. All right, so that is that's that. And next, let's look at section 9.2. So we're now on page 44. And now let's first look at this. We are going to consider some function called f of t equals the small f of t. Small f of a plus ht, b plus kt. Okay, that seems innocent enough, right? And then what we're going to do is we're going to calculate the f prime, that is the df big F by dt. So our first job is to calculate f prime of t. Okay, now big F of t, as we have stated, this is given, right? What is f prime of t? So let's calculate it the old-fashioned way. So it would be f1, okay, times h plus f2 times k, or if you write the whole thing out, it will be like over there with a plus ht and stuff still in there. Now we are going to set t equal to 0 in this equation, okay? Now once you have t equal to 0, of course you have f prime of 0 will be hf1 evaluated at ab, and kf2, okay? Same thing. Now at this point, I'm going to remind you that f1 is the same in this case, okay, as partial f partial a, and partial f2 is partial f partial b. Now you might wonder, why would that be? Because I thought a and b are constants. They were, but at this point we are going to turn them into a variable. Okay, and it is true, because originally when we defined the partial derivatives, we said that the f1 is taking the partial derivative of whatever variable that's in the first position, doesn't matter what. So we're going to take that reason, and now we're going to work backwards and call it f1 is partial f partial a, and f2 is partial f partial b, which is I thought it was quite a neat trick. Okay, and so anyway, so then f prime of 0 now will be called h times partial f partial a of a and b, and plus k in a similar situation. All right, so far so good, right? So that's where we got this thing in the book, the first sentence. Okay, f prime of 0, that's how we were taking the derivative of t, right? I mean, to start with, the function has something to do with t, and then suddenly we ended up with the partial derivative with respect to a and b, and that's how it happened. Now next, if we keep doing this, we'll end up with this equation. That's the binomial expansion that I mentioned earlier. Now the details, let me show you the details of how that actually happened. Okay, so then now so far we have gotten the first one, okay, f prime of 0 equal to that stuff, right? So then let's continue calculating the second derivative. The second derivative, of course, is calculated from this equation, where we have been doing that for a while, right? It becomes f11, f12 times h squared and hk and kh and all that stuff. Now, once you have done that, then you notice the f double prime of 0. If you plug 0 in here and using the same logic up here, then f11 becomes partial second f by partial a to the power 2. And I wrote the 2 on the bottom. It means to go on top. Okay, it's the second derivative, and so on. So this thing, as you can see, is starting to look like the binomial expansion, because the middle term, there's 2 of them, right? And then there's the end terms and all that stuff. It looks exactly like the binomial expansion if you put t equal to 0. So you get this thing. So that's why we need to know the binomial expansion, okay? And so that from that we will say that eventually the nth derivative will then become the thing that your book wants to claim, that this thing is true. As because the way we take the derivatives eventually, then we can do by induction or whatever, and that this relationship from the binomial expansion is true, where we do the n choose j trick. Okay, and so far so good. Now let's move on. Now I want to mention that then what we're going to do is we're going to write this thing, okay, easier without the summation sign in a shorthand form, which is this. Okay, this is intuitively the same as this thing, because this is the same as this stuff to the power n. Okay, and then we'll use this. So we'll use this as a shorthand for that. Specifically, I want you to change n to j, which is a simple change, right? And why are we doing that? Because we're going to need this formula, but in the form of j in a few moments. So as a result, please memorize this. I will call this equation 1, and I want you to memorize this equation for the next few minutes, so that if I say equation 1, then you remember I'm talking about this thing. Okay, so that's we will call that equation 1. Now, in the meantime, in general, fn plus 1 of t. So the second derivative, f double of t, is this stuff, right? And in general, based on this formula here, fn plus 1 of t will be this. Using the new shorthand that we arrived, it will be n plus 1 to the power of f a plus ht, b plus kt, etc. Okay, I got that based on this thing. Okay, now fn plus 1t formula, that we will call that equation 2, and I ask you to memorize that for the next 5 minutes or so. Okay, so that you know when I say equation 2, you know what I'm talking about. Or you can take a screenshot or something, or just go. Let's just move on. Okay, either way. But anyway, those are our 2 equations that we'll need later. Next, we are going to apply the Taylor theorem of one variable on the previous page. That is Theorem 11, and you don't have to look back because I have a copy and paste it right here. Okay, so that is Theorem 11, which we just proved, the one Taylor expansion for one variable. And now in this theorem, I want you to substitute a as 0 and x as 1. Now, if you do that, then f of 1, the little f, for this theorem only, will be equal to this. Okay, that is, it becomes fk power over factorial of 0, and then the remainder doesn't really change much, I don't think. Yeah, so that is from letting the remainder, of course, x becomes 1, so we got that integral there. So anyway, this is f of 1, where the f is just the f from the Taylor expansion. It is the general f. Now the next thing I want you to do is Okay, the next thing I want you to do is, let's see, I want you to substitute big F for small f in this equation and replace k with j, okay, because that's what the book uses. So we'll do that. So big F, being the small f is this f of 1, it applies for any function. It applies to our big F, okay. So let's plug big F in here. And then we have this particular equation right here. This is just a repeat of this equation, identical, okay. As you can, let me move it down a little bit so you can see better. And then, so plugged in word for word, big. So the only difference, we have a big F and a small f. And at this, so where are we right now? Now in the book, then we have come to let's see, yes, this part in the middle right here, okay, it has the exact same thing. We have f of 1 equal to that sum times plus that integral, right? In fact, I think that's where well, doesn't matter. I forgot, I should have just copied and pasted the book in here, but I wrote it by hand. It's the same thing, all right? So that's f1 equals to the sum plus that integral. Next, let's, what is this big F anyway? Big F of 1 is actually small f, the original small f, okay, not this one. That's just the one from the tailored expansion. But big F is the original small f we started definition with. What was small f? And remember, we started with big Ft, see, equals the small f a plus ht b plus kt on this side. See? So then this original small f, if you set t equal to 1, it will give us small f, a plus h, and b plus k. Okay, so that's our original little f. Now, having said that, and so then we are going to plug that in. So that, what does that mean? And now we're going to look at a whole bunch of symbols, okay? So then that means we are going to plug this equation, the little f will be equal to that stuff plus this stuff. Now, why is that? Well, first notice that the reason is because of equation 1 and equation 2. Because if this small f equals to that stuff, right? What is the stuff in red? The stuff in red is, as equation 1 puts it, is exactly this stuff, okay? And then as equation 2 puts it, the stuff in blue is exactly that. So everything match out. If you look at it, now please pause the video and look at this carefully and confirm that all things work out. That is, the small f is exactly this equation. And once you do that, then you will notice that we have just proved Theorem 12 right here, okay? So that's how we proved it. And then, so theorem, what is Theorem 12? Theorem 12 is the Taylor expansion for variables of two. Now we have expanded Taylor expansion to 2 variables, okay? So that's why it says f a plus h and b, f of a plus h and b plus k. Now we have one more thing to do, okay? Let's see. All right, so we just need to calculate the remainder. That's the next part. So here's our remainder, which we have done a little earlier, right? Where remainder is, the remainder is this thing. And so we'll write it down here. Well, the remainder is, the remainder is that part, okay? And so we will repeat it down here. And the question is then we need to show that this remainder can be calculated this way. Now we're going to show that by using, let's see, we're going to show it by using the theorem that we saw in the previous page, this thing, okay? We're going to pull it out and put something in there and pick a big X to show that so that we get rid of the integration sign. And to apply that, so I have the mean value theorem for integrals. I copied it right here so we can see it easier. And then we're going to let theta be the big X, okay? And then apply it to this integration. We'll yank out fn plus 1 theta over n. and then what's left is just the integration of that thing. Okay, and so and then when you do the integration part, you will quickly notice that it's equal to 1 over n plus 1 multiplied back in there, and then we get the Rn is exactly this thing right here, which and what is that thing anyway? So Fn plus 1 is, as we mentioned, this is equation 2, which defines what Fn plus 1 is. So we plug it in here, and then we get Rn equals to this thing as the book wants. And that is the second part of the proof of Theorem 12. So please do all this stuff yourself too, okay? And in other words, the book is just hitting the highlights of the proof. It's your job to explain every last bit of it, okay, to yourself, so that you have a full understanding of what this is about. So next, we are doing pretty good. Next, let's look at the bottom of page 45, where we talk about a useful way of presenting the Taylor theorem of two variables. Now let's look at this stuff. Okay, and what we're doing is replacing a plus h in the formula with just x, and b plus k will be represented with y. And if you do that, you will end up with equation what I call equation 3.5. The reason I call that is because the book has equation 3 on top there, and then equation 4 on the next page. But this equation says that it is useful. Well, no kidding. We're going to be needing this several times in the homework, and I want to give it a name, so let's call it 3.5. Now the equation, you might be puzzled as to you see the x minus 1 has a bar on top. If you don't remember what that means, that just means parentheses. Okay, it's a type of, that was taught in some math classes. In basic math classes, you draw a line on top, and that means parentheses, in case you don't remember. So that's all that is parentheses, okay? So x minus a is in parentheses, and then being the x minus a is h, okay? And y minus b is k, and they are in parentheses, and this formula will translate directly from the Theorem 12. And then we also said, we'll write down f of the little f at the end of the formula as r and s, where r is reasonably is a plus theta h, and then s is b plus theta k, and so on. So that is that. So remember, Theorem 3.5 it comes in very handy when you do the homework. Now let's go to the next page. Now, next page, we are going to let the Theorem 12 that we just proved, and let n equal to 0. If you let n equal to 0, then things collapses quickly, okay? All kinds of stuff disappears, and all you have left, now please confirm this, all right? All you have left is this equation. It equals to, we do the part where there's a theta in the theorem. That is the remainder is, well, this part, okay? We're going to be using this part. It has a theta in right here. It has a theta in it. Anyway, when you plug it all in and the dust settles and various things go to 0, it becomes 0, I mean, and we will end up with this formula right here, which is also quite handy. This is all happens by applying n equal to 0. So we get this one, which is similar to some equation we had earlier, but back then there was a theta 1 and theta 2, but this one doesn't, okay? So this one is nicer in that way because it has only one theta to work on. But so we'll use that conveniently. And so next, let's look at example A. Now, example A, we have a bunch of stuff, and what are we going to do? We're going to expand this thing by the Taylor theorem. So we're going to take all kinds of derivatives and then write the whole thing out. And as you can see, if you go through all that work, then you will have something that will that should come out. 45. Okay, so so please do example A, all right? And I have also done it, and it is tedious, but it's important that you do it because then it gives you a feel of expanding the Taylor series in the second with two variables. See, so I calculated all this stuff, And then I used, by the way, I used equation 3.5, okay, the very useful equation, as the book puts it. And then I wrote this stuff out like that, and that is what the book has. It also says that you can confirm it by doing the algebra here. And all I did is plug it into some algebra calculator, which I have the link below the video, because I wasn't about to do this by hand. Anyway, so that's example A. Example B is slightly different. Now, example A and example B will both be repeated in the homework, so please make sure you do them so you know how they're done. So example B, we have an interesting situation where f is C1, first smooth continuous first partial derivatives. G is also C1, and then f and g are both 0 at the origin. And then you have another condition where g as 0 is g1 as 0 plus lambda g2 is not 0 for some lambda. And then we need to calculate the limit as along the line y equal to lambda x. Not anywhere else though, just along that line, okay? Which should make it easier. So we're gonna apply equation 4 on top. So let's apply the equation 4, okay? Slap it right in here. And then you have, remember, y equals to lambda x. So when you plug that in, then you can cancel all the x's and end up with something like that. And then, and that's your answer. So pretty straightforward, I'd say, for this type of homework, okay? Yeah, so that's what I wrote down here. And I don't think I wrote anything the book didn't write. So anyway, you just, that is the answer, all right? So with that, we have come to the end of this section. And for homework, please do, let's see, let me turn the page of this thing. All right, for homework, please do problems 1, 2, 4, 8, 11, 14, 15, and 16, okay? And then, so yeah, please go do your homework then. And when you're done, I want to talk about all of them. Now that you're done with your homework, let's look at some of them. First, problem 1, which is it's a matter of plugging it into the Taylor expansion and the Taylor formula, which is what, Theorem 12, and then just evaluate everything and make it come out, I think. Right. So here's what I did for each part. Okay, part A. I did the grunt work and came out to be okay. And then part B, we have the same situation. Okay, we have all this stuff calculated. Let me check. Yeah, I think it looks right. Okay, that's part B. And then part C, the same thing. We just write out all the stuff, okay, according to the formula, and then and out comes this answer after you go through a whole pile of things. Okay, so that's problem 1. Now problem 2, we have a similar situation, I believe. We will expand this thing just like example A, okay, and then we will use equation 3.5 on page 45 right here. So then we just write this stuff out and work on it patiently, okay? And then I don't know why I write so much stuff, but I guess eventually I got it to come out right here. I think I made some mistake here, but I was able to fix it or something. Anyway, once you follow the formula, then out comes this thing, and it does equal to yeah, it does equal to the right answer, I believe. Okay, it does check out. And then again, I believe I used the algebra calculator to do the confirmation part, because I was not interested in doing that much algebra. Okay, and next, let's look at problem number 4. All right, we have, I think, a similar situation. We need to calculate theta. And problem number 4, we follow the formula of equation 4 on the previous page. Yeah, let's do equation 4 with that theta, the theorem with the formula with the theta in it, and then plug everything in, and then eventually, if you don't mess up, I think I messed up slightly, so I couldn't get it at first because I did some calculation wrong, but eventually I caught my mistake and was able to come up with the 28 instead of 29, so my theta equals the 1/2, just like it says. So that is problem 4. Now next, let's do problem 8. Now problem 8 sounds easily enough, right? We have EXY. E is always easy until I started doing the expansions and realized this thing is expanding fast. Okay, and I can't even see what I was doing. There are just way too many terms. So at that point, I decided to use something called the partial derivatives calculator. I have included the link below the video. In the video description below, and so I'll show you what I did. Okay, after I typed it into the partial derivatives, we have this giant mess. Now the first ones are easy enough, right? But then you have the second derivative and the third, and as you notice, the numbers are getting big fast. And remember, we are evaluating this thing at x and y equal to 0. So the only time these partial derivatives do not value as 0 is in these special cases. That is the fourth power, where partial derivative with even powers, and where you have a situation where you have a 2 right here, and then there's a multiply by x. So when you take the product rule of this thing times this, then you eventually knock it down to be a factorial situation. Okay, and similarly, let's see the third one. See, this gives us 3. Okay, and then the sixth derivative will be taking this one and knocking this thing down 2 times. So it would be 3 times 2, and so on. See, the fifth derivative, and then compared to what is that? The eighth derivative, you can take this one and then knock it down until it becomes 24. Is how that last term is obtained. And continuing, you notice a pattern. Okay, eventually it will be the 10th derivative, okay, down here, which the calculator did for me, because I'm sure as heck not doing that. So anyway, so the 10th derivative is, you can get it from this 6th one, which have a bunch of y's and 1 x, and then you take this thing and take this thing and do the product rule and knock this thing to 4, 3, 2, 1. So that's how you end up with 120, and that's how the factorial answer shows up. The reason I have done this part is because all the derivatives that's pure, that is, that's only have y in it, right? I start with so y3 and then y4 and y5 with just 1 x attached, which will give you the right numbers. All the other partial derivatives will end up being 0 because you can't get rid of the x's. So there's always some x attached to it. The only one that doesn't is when you when in the situation where you have x times exy, or x to some power times exy, then you're able to multiply it, and where things eventually becomes sensible. So please do this yourself. I know this looks like a giant amount of work. I mean, how did they do that back in the day, right? But I think they just, instead of doing all these partial derivatives, they just stared at it long enough and realized the pattern. And the pattern is that exy, then eventually we have only these numbers left, which are the factorial of situations. So, so that is the answer to our problem then, is eventually we realize that after staring at it long enough and looking for the pattern, we eventually realize that the only thing that doesn't end up being 0 is this partial of 2m f over partial xm partial ym evaluated as 0, and that equals to m factorial, and every single thing else will turn to 0 because we're evaluating this thing at 0. All right, so far so good. Now at that point then we will plug into the formula, okay, and so then exy, the formula for EXY in Taylor expansion will be this thing, and then eventually it'll be rewritten as from 0 to infinity of xj yj over j factorial. All right, and specifically the Maclaurin series, where y, if we set y equal to 1, e to the x in this case will become the xn over n factorial, which, as you might remember, is the Maclaurin series for e to the x alone. So that confirms that our formula is likely correct. Now, I should mention that the reason I have it divided by 2j down there is because only the even power remains in this equation. All the odd powers disappeared. So then I re-indexed it. Now that might sound slightly confusing. I'm following equation 3.5. Now, if that sounds slightly, just work through this yourself and you will see why this is the case, okay? And remember that being that all powers are gone, I re-indexed the counting, okay, instead of, yeah. Anyway, just look at it for a while if you don't know what I'm talking about. Or just work it out yourself. What would you say the answer is, okay? Knowing that all the odd powers have disappeared. And so that is that. So next, let's look at problem 11, which I think is similar to example B on page 46. So you just follow the rules of example B, okay? And everything will come right out. Calculate F1, G1, etc. and do the limit, and it does come out to be the right answer. I think problem 14 is the same thing. We have the f of x. We plug in example B again. So we have something that end up being that. Okay, and that is the correct answer as well. Now, that is both of them follow the examples in the book until we come to problem 15. Now, 15 has 3 variables. Now, there is something called cosine h and cosine h in there. If you don't remember the hyperbolic functions, don't worry about it. The cosine h, the only thing that's worth remembering about them, if anything at all, is that the derivative of cosine h is sine h, and the derivative of sine h is cosine h. And cosine h at 0 is 1, and sine h at 0 is 0. That's about all you need to know. And you can Google that, of course. But I've never found the hyperbolic functions to be the least bit useful in anywhere. Okay, now let's look at problem 15. But it has 3 variables, but in this whole section, we only have dealt with 2 variables. So I wasn't sure what to do about that, so I decided to just go back to our old trusted way of doing the L'Hopital's rule, because we're calculating some limit, and you can just tell that the limit is becoming 0 over 0. So how about apply the old L'Hopital's rule, and let's call it done. So that is what I did. I have what is that? Well, anyway, so I calculated the L'Hopital's rule, okay? And the limit, it becomes 0 over 0 by the time I was done. So that doesn't mean anything. We will do it again. Okay, so I calculate the second derivative, which end up being something. Because by the time you're done with I don't know what this is, basic calculus, and then we end up with f. I call the thing on top big F, okay, and the thing on the bottom big G to distinguish them easier. So by the time I'm done, the thing on top, second derivative, is f11 minus f2, and then I calculate the bottom is something similar. Okay, so I calculate, then I continue calculating the bottom and setting stuff to 0, and then I end up with f2 plus f33, and that is the right answer. So I will just stay with that and forget the rest. Okay, and so finally we are doing problem 16. So for problem 16, we have to prove this weird looking thing, okay? That we're going back a couple of sections before where we're proving the directional derivative, okay? The second derivative in the direction of psi alpha. And somehow we have to prove this relationship holds. All right, so that's what we're gonna do. And first we have we are going to use Theorem 9 on page 40. That is here are the conditions. Okay, F1, and F2 are all 0, so that's good. Now Theorem 9 on page 40 it gives the definition of how to calculate partial f partial psi alpha, which is that thing right there. And I'm going to call that equation g of xy, and to make things a little clearer. Okay, so then if that is the case, then g of ab will be 0 because f1 and f2 are both 0 at a and at ab. So from here, so then you can I first noticed that, and then we will calculate what partial g psi alpha is. That is, if g is that equation, we'll slap it into this thing again. Okay, and then which will give us the second derivative that we are looking for. So partial g partial psi alpha, once you apply this thing to g, okay, we will end up with this thing, right? Because then you have f1 becomes f11 cosine alpha, and so on. So once we get this of course is the same as partial square of f and partial psi alpha squared. That is, we'll call that equation 1 because that's what half of what we're looking for. Okay, so please memorize that equation for the next few minutes. And that is, so now we got to half of it, and let's consider the other half. Now the other half, we're going to go to Theorem 12. That is the Taylor expansion for two variables. And then I have a copy and paste it right here, so you don't have to look at it. Look it up, it's right here. Okay, now that we have it right here, I want to apply n equal to 1. Okay, that is, keep n equal to 1 in this equation and plug it right in. Then we'll end up with this equation right here. And then being that f1 and f2 are all 0 at a and b, then at the f of a plus h, b plus k will be equal to just the other half with the 1/2 in there. See that 1/2? Okay, where the values are evaluated at a plus theta h and b plus theta k. Now you notice what was that? That looks similar to what we saw earlier, right? And the equation that we're supposed to prove has 1/2 in it, which is why I did this to start with, because I realized when I put n equal to 1, I'll end up with some kind of 1/2, and I need that for what I'm looking for. So having done that, then we have, okay, now I have this equation rewritten, okay? Rewrite it as, I'll put the small h as a big H, and small k, I want big K to be small k. So I rewrote this thing, except I put H and K as capital letters. So then everything's the same, right? I just put H and K in capital letters. The reason is because we also have H and H in small letters, and it gets really confusing. So I shifted it into big letters so things are not so confusing. And at this point, then I say that big H is small h cosine alpha, and big K is small h sine alpha. Then we plug everything in. Okay, let this be true, and then plug stuff in here. That is, now big H is small h cosine alpha, etc. And plug these two conditions in here, and we get this thing right here. Okay, again, this is to be evaluated at the proper value. And in this, remember, now we have the h cosine alpha stands for big H, so we end up with this thing. Now, and things are looking quite familiar. So then the next step we're going to do is take the limit of this value as h goes to 0, right here. Okay, and then we're also going to divide it by h squared. Now remember, this thing has h squared all the way across. So dividing by it doesn't hurt a thing. Okay, so we got rid of the h squared, so we end up with this thing. And what is that? That is this. Okay, and that's exactly the equation 1 that we did a little earlier. I copied and pasted it down here, but it's the same thing. So we confirm that this part is exactly equation 1 with 1/2 slapped on. And so we have therefore concluded the proof. And that is also the end of this section.